Lesson 38, Neural Networks, Day 3. All right, so today's lesson, what we're going to do is eventually get to how to update our weights in our matrices and our vectors, given that we're going to use the 3, 2, 4, this node, this sort of arbitrary node network that I came up with as an example. And so what we want to do is we want to find out how, the good thing is, everything that we do in this lesson can be generalized to any number of nodes in your input, hidden, and final layers. So we want to just investigate what happens for this particular one, and I used it 3, 2, and 4 because it gave us different dimensions in our vectors and our matrices, and so we can see kind of how those things are lining up. Okay, so I have written everything out here so that we're not so you don't have to watch me write these things out and take all of your time. So what we're doing is we're given a piece of data. So for example, this one is xi, right? So your input vector to your input layer, right? So this the vectors that are coming in to your network, and that's the piece of data here. And then you're given some target. And I wrote those in red here so we can realize that that is our target that we're using to calculate our error. That's what we want this input to be. And this is just one row of data, and you would have many, many rows of data in order to get our network trained up. So if this is what our sort of network looked like, then out of that network would pop, the things that would pop out of this thing would be, the first would be that vector that represents our I bias vector, our WIH matrix, which represents the weights that are on going from the input layer to the hidden layer. Again, remember, this WIH matrix has the number of rows that correspond to the number of input nodes, and it has the number of columns corresponding to the number of hidden layer nodes. So that's where these things come from, and you can kind of see them up here and where they're going into. And then our WHF, again, the number of nodes in your hidden layer would be the number of rows in your WHF matrix, and the number of final layer nodes is the number of columns that you would have. And the H bias is the vector that has the number of rows of your number of nodes in your final layer. And you can see kind of how these things line up. The error that's in your final layer is a simple subtraction. So you just take your target. So again, that was these red numbers up here, and you just subtract off whatever's popping out or coming out of your final node of your final layer. So I'm just the output node, the output vector of your final layer. There you go. And so those are the numbers that are coming out, and then it's a simple calculation in order to get that error. So now what we want to do is we want to use this error in order to train our network. And how do we do that? Well, let's remember a little bit of the forward propagation and the backward propagation. That was the subject of last class. And so the output vector of your input layer is simply these two vectors are equal to each other. We saw that our input vector into our hidden layer was simply our transpose of our WIH matrix times the output of your input layer added to your I bias vector, and this was the multiplication. This is what it came out to be. And we did this one actually in the last video. And then all you need to do then to find the output of your hidden layer, the vectors coming out of those two nodes, in this particular case it's just two nodes, is just to take the sigmoid function of these numbers that come out of that one. And then the final thing, yeah, I didn't put a vector sign over the top of it. I'll go ahead and do that real quick. Yeah, it's not allowing me to do it for some reason. Huh. Maybe I got to get out of it and get back in it. So let me exit out of here. Stop sharing. Go back to OneNote. Share it again. Come back down. And all I want to do is put a vector sign over the top of my X, because it is, in this particular case, more than one number. All right, so it allowed me to do it now. And then all we would do is, in order to find that vector, So again, that's the things that are coming out or coming into your final layer here, those 4 numbers there, is just to take the transpose of your WHF matrix, multiply that by the output of your hidden, these 2 numbers here, and then add your H bias, which is this piece here, and then we'd add those numbers up and we'd get, and this is the sort of the, go back to the individual W01 plus, I mean, if you're multiplying the weights times the numbers that are going into it, and adding all those things up, you would get that vector. And then that's your forward property. Oh, I'm sorry. The last one would be, what is the numbers that come out of your output layers, I'm sorry, your final layers output vector would simply be the sigmoid function or your activation function of your input. And then we come over here and we see what the back propagation was, and that's the last thing that we talked about last class. The final layer for each one of those nodes, all you do is you just subtract. Again, it's just right here, and it's what I call EF1 through EF4, and then the error associated with each one of your nodes in your hidden layer, right? So what we're talking about is the layer, or I'm sorry, the error that's in each one of these 2 nodes is your WHF matrix times EF, and that's all we're saying there is we're getting rid of those proportionality constants, so to make our life a little bit easier, and we're proportionally, so go back to last video, we proportioned the amount of weight that we assign to each one of those errors. Okay, so now what we want to do again is use this error in order to update our weights. In order to do that, we need to understand the gradient descent algorithm. All that means is if you want to, so here's an example of how you would use the gradient in order to incrementally step towards a minimum value. So that's really what we want to do here. So think about what we're talking about up here. I'm using this error function, I'm going to turn it into a bunch of functions here in a second. And then what we want to do is we want to use those functions to incrementally go towards the minimum. In other words, if I chose a different W values, these would be the W values that would make the difference between the target and the output of your final layer as small as possible. And so that's what we want to do. In order to do that, again, we got to realize how to do that. And the way that you do it is you utilize the gradient. And so in this picture, what I've given you is a starting point. So the green is the starting point. So we start at this particular point. And then if we calculated the gradient, we know from calculus what that looks like. We know the gradient actually points in the direction of maximum increase, which is orthogonal or perpendicular to these contour lines. And so this W1, W2, this number, this point here would sit, if it sat on that contour line, we know it would actually point in the other direction. But I don't want to go towards the maximum. I want to go towards the minimum. Again, this blue star represents the midpoint for this particular function. In other words, it's like it's going into like a hole. So this would be a lower, like if you want to think about it as a map, this would be like a lower elevation than maybe somewhere up here. So you kind of you'd be going down. And the way we would use the gradient is we would, instead of going towards maximum, we'd multiply by -1. So that just makes the direction go in the opposite direction. And then we would basically go in some smaller step. And so I didn't include that on here, but what you'd want to do, and I'm going to go ahead and write it in here, is I want to have some h or some little step size, and we'll call it step size. I want to have some sort of, I want to go in that direction, but I don't want to go a full, like really, really far. I want to incrementally go towards this answer. Why? Because if you took too far of a step, you could actually get worse. So if you incrementally, right, because that's really what the gradient is, it's all about instantaneous rate of change. And so if you took a step in that direction, small step in that direction, then you'd be getting better. And that's what we want to do. All we want to do is, for every piece of data, is we want to incrementally get better and better and better every single time. And so if I had a whole bunch of data, I would maybe take a little bitty step, little bitty step, little bitty step, and eventually we would be able to get to our minimum. And that's the idea. So Notation wise though, I'm using this next here. So this would be W1, W2 would be my next value that I would use for W1 and W2. And that would, this piece would be my green. And then I would take this little small step times my gradient. Matter of fact, times my negative, or whatever my delta 1, delta 2 is, where that delta 1 and delta 2 represents the negative gradient. And that's how you would get that particular direction. So all I'm going to do now is I'm going to do what it says right here in this line. I'm going to go to our notebook and I'm going to show you why you always want to go, why you want to take small steps in the first place, right? Because I could show you that in here. Like if we made this green vector really, really large, it wouldn't be good for us. But I'm going to show you why we want to take small steps, and I'm going to show you why we always want to go in the negative gradient, or in this case, we're going to do it a single variable function, so it's just going to be a derivative. So let's stop this. Let's go to our notebook. And this is the R notebook associated with today's class. All I did was I brought in our f prime function that we've already developed in our class. So I'm going to go ahead and shift enter on that one. I'm going to bring in this function, and a very simple function, x squared plus x. All I want to do is I'm going to go to, and then I grafted, that's all this next little piece is. And then I'm giving it a xm is going to be our starting location. In this case, I started at 3. And then you can read all this whenever you open up the notebook. But basically, what we're doing is we're gonna make step size really, really small, 0.1, 1/10. And then I'm gonna start. So this would be my xm current, and then I'm going to update it by going in the direction of the negative derivative. So a really small step, and that's what the step size represents. I'm going to take this small step in the direction of the negative, and the reason why it's negative because I get a -1 there. And this is the derivative. And then we printed it off, and so shift enter. You see it's negative, 2.3. So we started at 3, I believe. Yes, we started at 3, and then we took a step in the direction of the minimum. And you can see that it's going in that direction. Okay, so if we kept running the code, we would get something. So I'm going to experiment with it. So you can come here. Again, feel free to do this in your R notebook. Start in different places and take a different step size. I'm going to leave the step size as 0.1, control enter, and then I'm going to take 50 steps. And so that's what this next piece does. It takes 50 steps, and it shows you if we started at 4, our next step would be 3.1, our next one would be 2.3, and it just kind of goes and goes and goes until we get really, really close to what I think is the actual minimum, which is negative 0.5 or negative 1/2. So you can see that that if you move in the direction of the negative, actually, you can't see that. Maybe we want to, let's try, maybe this is just a fluke. Let's try negative 5 and see what happens. And so again, if you're on the other side of the minimum, right? So now I'm starting over here somewhere. I want to know if it's still going towards my minimum by using the negative gradient, and it does, right? So you can see now it's coming from the other side, from the left, if you will. And it's getting closer and closer and closer to negative 0.5. Okay, that's all I wanted to show, that the fact that we're going in the direction of the negative derivative in this case, but when we get to multivariable, we're going in the negative gradient, that sort of makes sense. That's all we wanted to show there. Go back to OneNote. And so your next question, hopefully, is, well, how do I use this idea and this error up here in order to do that, right? So I want to make my W's as good as possible so that this error is small as possible. So we're going to come back down, and so again, that's the next question there. How do we relate those two? And it talks about this squared function. Now, why do I want the square function? Because I don't want it I want to have the absolute value, if you will, and EF squared is the way of getting that. In other words, I don't want it to be a big negative number. I want to minimize it by making it as close to 0 as possible. And so that's why we squared this term. But basically, this function becomes, these EF squared functions are a function of W01, W02, W11, W12, W23, and so on and so forth. So these become a multivariable functions, because it's more than one function, right? It's 3 of them. So it'll be T1 minus OF1 squared will be a function. T2 minus OF2 squared would be a function. EF3 squared would be a function. EF4 squared would be a function. But they're each one of these functions has some W's that are associated with them, and that's the point of the next piece. We want to figure out what those W's are, and then once we do that, once we figure out what those are, we're going to use the fact that all I'm going to do is take the partial derivatives and move in the direction of the gradient. So that's what we want to do. That's what I'm trying to set up here, is that I know the next WHF, the WHF next, if you will, is equal to my current one plus this delta WHF, where this delta WHF is a matrix of negative gradients. Where, and here, it's just the partial derivatives with respect to some Wi comma j, where I and j are the row and the columns in that WHF matrix. So let's find it. Let's find this delta WHF. And the way that we do that is we just set it up, right? For this 3, 2, 4 network, I'm going to come in and I'm going to say, well, EF squared is just each one of these terms squared. And then I'm just going to substitute in what the calculation in our forward propagation does. So for example, or our error, right? So in this case, it's our error term is just T1 minus OF1. And then, well, I know what OF1 is, right? So I know how to calculate OF1. Well, that's just the sigmoid of XF1. So just take a second to think about that for a second. So I start off at squaring each one of these components of my error of my final layer. So that's the first node of my final layer, the second node error of my final layer, the third node error, and so on and so forth. And I'm just squaring that error. And then I'm taking the target and subtracting the output of my final, right? So that's how we get this number. And then we know, well, I know how to get that number. I'm just going to simply take the sigmoid of the input to my final layer for each one of those nodes. And then if we remember, right, so again, this recall, this matrix multiplication here, I know what XF1, XF2, XF2, XF3, and so on and so forth. I know how to calculate those. It's just WHT times OH plus my H bias gets me these numbers. So this first row in this vector corresponds to XF1. The second row in this vector is just XF2. So all I'm doing now is I'm taking these numbers, this vector, if you will, and I'm taking it and I'm substituting it in here for XF1, XF2, and so on and so forth. So you see, if you just read this off here, it's the same thing that's over here in this vector. But the note here, so note that the error in node 1 of the final layer is a function of W01, W11, and W21. And those are the things that we want to update. So now we're sitting in a spot where I can start taking some partial derivatives and use those partial derivatives in order to come back and update my weights. So it's a function. So this first one is f1 of W01, W11, and W21, and is equal to E1 squared. And then the second one is a function of W02, W12, and W22, and so on and so forth. And you can kind of see from just by using forward propagation how we come up with these functions and what I need to take the partial derivative of in order to find what I need to do in order to update my weights. So I claim that this delta WHF is simply the partial of EF1 squared, right? That function, this guy right here, with respect to W11. And the second piece here is the partial of the same, I'm sorry, not the same function, the second node with respect to W12. And if we want to stay on W11, it's this one and this one, right? So I'm taking the partial respect to W11, the partial respect to W21, and that becomes my direction to decrease EF1, that first node of my error I'm sorry, the error of my first node to the final layer. This would be the direction that I would need to take WHF in order to make it as small as possible. Remember those little small steps. And this one would be the one that I'd want to go if I want to try to decrease node 2. And this would be the direction that I'd go if I'm trying to decrease node 3. And this would be the direction that I'd go if I'm trying to decrease node 4. So I'm going to use that, and once we've calculated it, it's going to be my delta 11, delta W2, my delta W11, my delta W22. So these things are what I need in order to figure out what goes into this guy right here. Again, you guys could watch me write this stuff out, but I just don't think it's worth that amount of time. In class, we're going to program this thing. We're going to come back and we're going to do the things that I'm talking about in here. But for this, to understand what's going on, you need to at least walk through this. Okay, so now I'm going to calculate these things, right? So we're going to go use the rules of differentiation and calculate it, right? So it's mostly chain rule, but you'll see that we actually have to do it, right? So this next piece is choose one. So I'm just going to choose one, and then I'm going to show you what you have to do to calculate one of these, and it's going to hopefully become very obvious how to do the rest of them. So for this one, we're going to choose row 2 and column 3. So I'm going to choose this guy right here, and I'm going to actually calculate this using the rules of differentiation. In order to remember, right, so I'm going to take the partial of EF3 squared. To remember what EF3 squared was, I just take this guy here, and I moved it down right there. So all I did was copy paste it down there. All right, so when we're taking the partial derivative, so it's the partial of EF with respect to 2, 3, so EF3 squared with respect to W23. Remember, you got to you take the 2, multiply it by the front, and then whatever is in the inside, right? Chain rule stuff. And then so that's what's in the inside. And then multiplied by the derivative of the inside, right? So what's the derivative of the inside? Well, it becomes a -1, so that's where your -1 comes. And then the sigmoid function, remember from yesterday, the sigmoid function has a really neat derivative. And I'm going to write it out here because I forgot to right here. So it's sig prime of x is equal to the sig of x, and we showed this yesterday, times 1 minus the sig of x. All right, so that is the formula that we're using to take the derivative. And you still got to do the chain rule, though. So in this case, we have the sig of that guy, then 1 minus the sig of that guy, and then this is just the chain rule done another time. So now we got to take the derivative of the inside. And so the derivative of the inside now is just, where is there a W23? Well, there's only one on that term right there, so you're just left with an OH2. All right. So in a few minutes, we're going to do the I bias, or we're going to take the partial, and we're going to the partial with respect to W03, and we'll see that everything comes out exactly the same, except when I'm doing this last piece, when I'm taking the derivative of the inside, there is no term on the W03, so that becomes a 1, and we're just left with a 1 here. So you'll see all of this other stuff remains the same. It's just I got a 1 right there when I'm doing the bias node. Or the bias weight, I should say. The weight on the bias node. Okay. So now we got to simplify, right? So the cool thing about this thing is it sort of just simplifies out into something very, very easy for us to take care of. The first thing is I don't really care about the 2, and I guess I didn't mark that sucker off, but I'm not really concerned with the 2 here because I have a, I have a learning rate, and I'm not really upset that there's a 2 running around on there. We also find that T3 minus sig, the sigmoid function of this thing is just EF1. Why is that? Well, because the sigmoid of this guy is just OF3, and T3 minus OF3 is just EF3. So we know that this whole thing inside here just becomes EF3. And then we get rid of that negative sign because we know we want to go in the negative direction because we're worried about the negative gradient, right? We're going towards the middle, or I'm sorry, the minimum. And then we know this is OF3. And this one is OF3. and this guy is whatever it is OH2. So now I'm going to take these simplifications and write those into a matrix. Well, first I'll just write it as delta W23, right? So it just becomes EF3, which is that piece, OF3, which is there, 1 minus OF3, which is that guy, and then OH2, which is there. Note that the indices align for the row and column. So all I was saying there was, this means, right, so let's go back up, column 3 of my delta WHF matrix better have this term, column 3 and row 2. So you go to column 3, row 2, and that is the one that lines up with this W23, right? So this should be W23. And then if you did this same process and chose 1, 1, 2, 1, row 2, column 1, row 1, column 2, row 2, column 2, and so on and so forth, you would get all of these values that are in this matrix. Now what I want to do is I want to look at this matrix. So if you looked at this matrix and you said, you know what, I can make this matrix happen a lot easier than having to sit here and do all this stuff. There's an easy matrix multiplication that we can do. Matter of fact, I sort of said called it an outer product. So if you ever mess around with inner products, you know that's the dot product, if you will. But the outer product actually makes matrices, right? So it makes these rank 1 matrices. And so this would be OH1 and OH2. So it's a 2x1 matrix. And then I take the vector. So that's not a matrix, but a vector. So 2x1 vector. So it's a column vector times a row vector will give me a matrix. So the vector that's associated with the row vector that I need is the EF1, OF1, 1 minus OF1, right? So that's the first component of that one. And then this would be the second component, the third component, and the fourth component. And then if we multiply these two together, we would get this matrix. So this is kind of neat because now I can just express delta WHF as 2 vectors. So I'm going to take my EF vector, my OF vector, and my EF and OF vector, and I can produce this thing and turn it into a row vector, and then I can have my OH1 and OH2, my OH vector, and we can do this multiplication and make this delta. So it becomes a very quick thing that we can do. So let's figure out the bias, and I think I've covered the bias when we were talking about the only difference between the I bias. I'm sorry, we're doing H bias, right? So we're doing H bias in this case. The only thing that's different is there's a 1 here instead of OH. I think it was 2 up there, right? So it was OH2, yeah. The only difference is there's a 1 here, because when we go take the derivative of the inside, when we apply that rule again, we end up getting in here and having a 1 in there. So now we simplify it again, and you end up with exactly the same vector, this EF1, OF1, 1 minus OF1, that was this row vector here. So what I think we should do is produce this thing, let it be delta H bias, and then take the transpose of H bias, throw it down there, and then multiply it by OH1 and OH2, or the vector OH. So that's what we will end up doing. And then if you do this for delta WIH, so that's the other thing, is we could keep this same idea and do it for WIH as well, right? So use the same calculations, except instead of having EF being my final, I have EH. We can find delta WIH and delta I bias. And so in that case, instead of having OH here, I have OI, right? Because that's the input into my, or I'm sorry, the input into my, output of my input layer. Yeah, it gets confusing there. That's one of the reasons why I changed final layer to output layer. But it's the output of my input layer. So that's the vector that's coming out of my nodes, which is also the input because they're equal. And then times this guy here. Where did I get that guy? Well, it's just the I bias. And it comes up here, and we can do this multiplication. All right, so again, that ends this lesson. I know hopefully it was pretty quick. There's a lot of calculations on here. What we're going to do next class is we're going to use, we're going to use these calculations in order to produce some R code that's going to help us out. All right, that's all I got, and I'll see you guys in the next class.